Okay, so let's do an example. Let S be a parallelogram with vertices at P0, 1, negative 2, 3, P1 equal to 2, 3, 5, P2 equal to 5, minus 6, 7, and P3 equal to 6, minus 1, 9. Verify Stokes' theorem when F is Zxi component plus 2x minus yj component plus y squared k component. Okay, so let me first graph this parallelogram. So let me do that. Okay, so I've graphed a parallelogram here, and I'm going to look for a mapping, a fine transformation R that maps the unit square onto my parallelogram. So I know I've graphed this somewhat right here because let me just show you that the P1 minus P0 would be this vector here. That should be parallel to the P3 minus P2, so you can check that to make sure you've drawn it somewhat accurate. So let's check that. So now have a look at P1 minus P0, so it'll be this vector here. So P0 is 2, 3, 5, P1 is 2, 3, 5, minus P0, 1, minus 2, 3. So it'll be 2 minus 1, so it'll be 1, 3 minus 2, so 5, 5 minus 3, 2. Then if I do P3 minus P2, P3 is 6 minus 1, 9 up here. And then minus P2, P2 is 5, minus 6, 7. Subtracting those, we get the same 1, 5, 2. It means that this side is parallel to this side. Okay, so that means we've graphed our parallelogram somewhat accurate. Okay, so let's keep going. So looking for an affine transformation now that maps this unit square onto our parallelogram. So here's my affine transformation formula. So let's make it so, say 0, 0 gets mapped to P0. So let me write that here. Okay, so my R of 0, 0, I want to go to P0. P0 is the 1 minus 2, 3 up here. So putting 0 in place of U and 0 in place of V all the way across here, this now will become C1, C2, C3. Let me write that. Yeah, so putting 0 in place of U and V, you'll have C1 here, C2 here, C3 here. So you'll have then C1 has to be 1, C2 has to be minus 2, C3 has to be 3, which I have here. So now we replace these guys with those values. Okay, so if we replace the C1, my C2, and C3 with these values, now let's say map the 0.10 onto say P1. So let's write that here. Okay, so this. So I'm going to put 1 in place of U up here, 0 in place of V all the way across. So 1 in place of U, 0 in place of V. So let me do that. Okay, so we'll get then, so again, putting 1 in place of U, you'd have an A1 there, 0 in place of V, so you have A1 plus 1 on the first component. Then putting 1 in place of U here, you have A2, 0 in place of V, so it'd be A2 minus 2, and then you get A3 plus 3 in this one. So you'd have A1 plus 1 equals 2, that means that A1 would be 1. A2 minus 2 would be 3, adding 3 to both sides, you'd have A2 is 5. And A3 plus 3 equals 5, that means that A3 would have to be 2. So let me replace those up here now. Okay, so I've replaced my A's up here. So next, let's map the R01 onto, say, P2 over here. So let me write down here. So look at this then, so R01 goes to P2, and P2 from up here is the 5 minus 6, 7. So putting 0 in place of U, 1 in place of V, you'd have B1 plus 1. 0 in place of U, 1 in place of V, you'd have B2 minus 2 here. 0 in place of U, 1 in place of V, B3 plus 3. Okay, so then we can solve for these things here. So B1 plus 1 would have to equal 5, that means B1 is 4. And B2 minus 2 equal minus 6, that means B2 would be minus 4. And B3 plus 3 equals 7, that means that B3 would have to be 4. So let me write that here. So I've written those here. Now I can replace them up here now. I'm going to replace the B1, the B2, and B3 with these values. Just do that. So replace the B values up here. So you might say, well, hold on a second, we found all the values now, but how do I know the fourth point is going to work? Well, it should. If since it's a parallelogram, it should be forced to work. we can check it now. So R of 1, 1 should end up being the P3 guy. So let's check it here. Okay, so I'm doing my R of 1, 1. So 1 in place of U, 1 in place of V, all the way across. So you get this then. And when you simplify that, you get 6 minus 1, 9, which is P3. So it works out. Okay, so we found our mapping now. We've parameterized our parallelogram. So now let's keep going. So summarizing, we've parameterized our parallelogram we'll be using our D region, and this is my f function. So here's Stokes' theorem. So we're trying to verify this. So we have two parts here. We got the line integral on this side, and we got a double integral over S on this side. So I'm going to work on this double integral part first. So let's do that. So to find the flux of the curl of f across S, we'll be using this formula we developed in 15.6. So this formula requires us to find RU cross RV and also the curl of f. We need to find out also. My f's up here. So let's work on the RU cross RV first. Okay, so RU derivative with respect to U. So the first component derivative with respect to U would be 1. Second component it would be 5. Third component would be 2. So I got this guy. Then derivative with respect to V. The first component would be 4. That'd be negative 4. That'd be 4. Now let's cross these. Here's my definition of cross product. So let's do the I component first. So it'd be 5 times 4, so 20. Minus a minus 8, so it'd be 28 in the I component. Then we'll do the J. So it'll be minus in front here, and that'll be 1 times 4, so it'll be 4. 2 times minus 4, so it'll be minus 8 here. J, and then the K one. 1 times 4 would be 9, so plus minus 4. And then minus 5 times 4, so minus 20. That'd be K. Hence this becomes this. So now let's do the curl next. So I'm going to write the definition here. So there's a definition of curl. So again, I use my function down here. The functions up here is to be zx here, 2x minus y here, y squared here. Okay, let's do the I component first. So the partial y acting on y squared minus partial z acting on 2x minus y. So we get this. Now let's do the j one next. So j will have a minus sign in front. It'll be partial x acting on y squared, partial z operator acting on zx. So let's write that over here. So we get this then. And lastly, we'll do the k component. So the partial x operator acting on 2x minus y minus partial y operator acting on zx. So we write it down here. So we get this then. So looking at the I one, the partial y operator acting on y squared will become 2y, and there's no z in this, that'll be 0. So we write that down here. Next, the partial x operator acting on y squared will be 0. Partial z operator acting on zx will just be x minus x, but there's going to be 2 minus signs, so it'll be plus 10, so it'll be plus x here. Okay, so I've written it here. And then lastly, partial x operator acting on 2x minus y, that would be just 2 on that one. Partial y operator acting on zx would be 0, so it's like going to be 2k here. Okay, so here's my curl. So we got everything we need now to start doing the double integral. So let me erase some things and summarize what we have. So summarizing, we got this. So my curl here and my RU cross RV. So again, here is the double integral we're integrating. So we're using this formula here. So we're looking at curl composed with RU of V. So that means that's going to be your x, that's going to be your y, that's going to be your z. When you plug into this guy here, it's going to be 2 times y, which is that, plus x, which is that, plus 2k. And then dot it with this guy. So let me write that down here. And our D is this region over here, so it's going to be from 0 to 1, 0 to 1. So let me do that. So look at this. So again, that's 2u, that's my u. I'm plugging into this, and plus x, which is u plus 4v plus 1 right here, and plus 2k dotted with this guy. Okay, so let's do the dot product now. So it's going to be 28 times this guy here. So 28 times 2 is 56. It'll be 56 there. And 4 will go in front here. And it'll be minus 24 times 2 will be minus 48. So let me write that down here. So look at this. So then the 56 multiplied in there. Multiply the 4 in here. And then combine like terms. So I'll let you check. You can pause the video and work this out. But this is the result you should get right here. So it should be 284u minus 208v minus 156. Okay, so integrating with respect to u, so it's going to be 284u squared over 2. So that's going to be 142 then. U squared then is going to be minus 208vu minus 156u. So let me write that over here. So after integrating, we get this then. So it'll be 142u squared minus 208uv minus 156u. So we're going to put 1 in place of u and then 0 in place of u. So let's do that. So doing that, you get 142 minus 208v minus 156, which reduces to negative 208v minus 14. So let's integrate this now with respect to v. So it'll be v squared over 2 for this guy, and it'll be negative 14v in this guy. So let me write it over here. So look at this. So then evaluating at 1, you'll have negative 104 minus 14, which is negative 118. Okay, so that's the answer from the double integral side. So to verify Stokes' theorem, we still have to show that the line integral around C, line integral of f around C is this number also. I'm going to do that in another video, so let's leave it here on this video. So in part 2, we'll show the line integral also gives us this. Okay.